Welcome back. Let's talk about calculating the pH during the titration of a weak base by a strong acid. So the titration of a weak base by a strong acid is going to be very, very similar in the process to solve it as what we had for a weak acid. We're just flipping acid for base. And so the same starting question has to be asked at every moment throughout a titration. What is in the beaker? What is in the flask? That's what's going to determine your pH. There are 4 different times still that we're looking at the pH: before the titration has begun, before the equivalence point, at the equivalence point, and after the equivalence point. Before the titration begins, the only thing we have in solution is the weak base. And so we're going to solve a weak base equilibrium problem in order to find that pH. After the titration has begun, but before the equivalence point, we're going to have some of the weak base having reacted to form its conjugate acid. So we'll have a mixture of the base and conjugate acid. This is a buffer. We have a weak acid, weak base, both present in solution. At the equivalence point, all of that weak base will have been converted to the conjugate acid, so we'll have to work a weak acid problem. And then after the equivalence point, we're going to have excess strong acid. If we look at what the predicted pH would be, initially we're starting with just a conjugate base. We'd expect the pH to be relatively high. And then as we begin adding strong acid, we're going to see that pH drop. And then once we enter that buffering region, we're going to see the change in pH slow. Once we reach that equivalence point, we're going to see a sudden change in pH. And then that pH is going to level off once we have excess acid, and it's the excess acid determining the pH. And so if we identify all those pieces, we've got our weak base to start with. We've got a buffering region where we see a relatively slow change in that pH. We have our equivalence point, the steepest part of that curve, where we are going from a curve that is concave up, or excuse me, a curve that is concave down to a curve that is concave up at that inflection point. And then at the end, we have our excess strong acid. If we take a closer look at that equivalence point, we'll notice that if you've used up all of the initial weak base that was present and the strong acid that was added in that 1-to-1 ratio in this case, or in that stoichiometric ratio in a more general case, all we have at the equivalence point is the conjugate acid and water. And so since what we have in solution is a conjugate acid, our equivalence point is going to have an acidic pH. And so we will see an equivalence point whose pH is below 7 when we are titrating a weak base. If we go through the math, we're going to begin by working a weak base problem. Here again, the only thing I have in this solution is the ammonia and the water. I haven't started adding anything else. My volumes aren't changing, so I'm going to use an ice table directly here for my base equilibrium problem. I do need to know the Kb value for ammonia, which I look up in a table and to find to be 1.8 times 10 to the negative fifth. And that will allow me, recognizing that a small amount of this is going to dissociate, to calculate the concentration of hydroxide and therefore the pOH and pH at equilibrium. And so you'll notice that our initial starting pH is 11.13, so it is basic as we would predict. When we begin adding hydrochloric acid, we need to start by looking at our balanced chemical equation between the ammonia and the hydrochloric acid. Because hydrochloric acid is a strong acid, this reaction is going to go to completion. So I'm not going to use an equilibrium arrow. I'm going to use a regular arrow because any reaction containing a strong acid or a strong base is going to go to completion. And because the titration has begun and the volumes are changing, I'm going to use a BCA table. So when I look at this BCA table, I'll see that I have no hydrochloric acid left. It was completely consumed. I have chloride ion formed, but that's a spectator. I have ammonia and I have ammonium. That's an acid-base conjugate pair, and it's a weak acid-base conjugate pair. And so that means that I have a buffer, and I can use the Henderson-Hasselbalch equation. Before you start plugging things in blindly, please notice the Henderson-Hasselbalch equation is in terms of pH and the pKa. So I actually have to stop and find the Ka so I can find that pKa. Once I found that pKa, then I can plug it in and use the Henderson-Hasselbalch equation, keeping track that my base form goes on top and my acid form goes on the bottom. And you'll notice that the pH is 9.44, which is a little more basic than the pKa, which makes sense because I've got a little more of the base form of the buffer than I have of the acid form. If I continue to add additional acid, again, I need to start again by saying what in total have I put into my flask. And I'll notice that at this moment in time, I have stoichiometric amounts of NH3 and HCl. It's a 1-to-1 mole ratio, and I've got the same number of moles, so this is my equivalence point. So again, at the equivalence point, we ask ourselves, what do I have in solution that's going to be changing the pH? Well, chloride is just a spectator, so the only thing I have left is ammonia. And it's in water. When ammonium's in water, that's a weak acid. So I need to carry out a weak acid equilibrium problem. And for those weak acid equilibrium problems, remember, it's easiest to work in concentration. So I will convert my moles of ammonia into a concentration of ammonia. And since we have a very small Ka for this reaction, it's very safe to assume that X is much, much less than 0.05. And so we're going to neglect it as we solve the algebra on this problem. And so the pH at the equivalence point is going to be 5.28, which is acidic, which we would expect because we formed a conjugate acid. Last bit, let's keep adding acid to this reaction. Once again, every time I look at a new point along my titration, I'm going to start by asking myself, what have I added in total up to this point in time to my flask? And if I look at what I have after these chemicals have reacted, I have chloride, which is a spectator. I have NH4, which is a weak acid, and I have HCl, which is a strong acid. And the strong acid is going to determine the pH of this solution. And since HCl is a strong acid, the concentration of hydronium will be the same as the concentration of the hydrochloric acid. So I'll take my moles, divide it by the total volume I have in solution to find the new concentration, and then take the negative log of that value to find the pH.